Hello students. The objective of this lecture is to understand the properties of discrete time Fourier transform. So as you all know, the discrete time Fourier transform, or simply DTFT, is the member of the Fourier transform pair which operates on the discrete time aperiodic signal. And the mathematics of this discrete time Fourier transform can be understood by stating the synthesis and analysis equation of the discrete time Fourier transform. So consider a discrete time sequence x of n. We can represent an aperiodic signal x of n by its Fourier integral, and that Fourier integral is given by the expression x of n is equal to 1 by 2 pi integral over 2 pi x of e raised to j omega e raised to j n omega d omega. So here this x of e raised to j omega is the Fourier spectrum, and this integration is over 2 pi. That is, we can integrate it over any continuous interval of 2 pi. We can integrate it from 0 to 2 pi or from minus pi to pi. And the spectrum x of e raised to j omega is defined by x of e raised to j omega is equal to summation n from minus infinity to infinity x of n e raised to minus j omega n. So the Fourier transform x of e raised to j omega is the frequency domain description of the discrete sequence x of n. That is, x of e raised to g omega is equal to DTFT of x of n. Similarly, the x of n is the inverse discrete time Fourier transform of x of the spectrum x of e raised to j omega. So symbolically, this can be expressed as the Fourier transform pair. So we can say that x of n and x of e raised to j omega constitute the discrete time Fourier transform pair. Next, let us discuss about the nature of the Fourier spectra. So this is the most important property of the Fourier spectra. So Fourier spectra are the continuous function of omega. So x of n is a discrete time signal, but its Fourier transform, that is Fourier spectrum x of e raised to j omega, that is its DTFT, is a continuous function of omega. So this is because the omega is a continuous variable. That is, omega can take any value over a continuous interval from minus infinity to infinity. So this can be explained using the extension of the discrete time Fourier series concept. So in a discrete time Fourier series, we are representing a periodic signal, discrete time periodic signal, as a sum of the everlasting exponential. So in DTFT, actually, we are extending this representation, the representation of a periodic discrete time sequence as the sum of the everlasting exponential. So that representation is extended to an aperiodic signal. So to represent an aperiodic signal x of n by this everlasting exponential signal, actually first we will construct a new periodic signal from the aperiodic signal x of n. So that periodic signal x n0 of n is formed by repeating x of n over n0 unit. So this is explained in this figure. So here you can see an aperiodic sequence x of n, and by repeating that aperiodic sequence over n0 with the period n0, actually we construct a periodic sequence. So from the aperiodic sequence, we are constructing a periodic sequence xn0 of n. And here this period n0 is made very much larger to ensure, to avoid the overlap between the repeating cycles of this xn0 of n. So a periodic signal xn0 of n actually can be expressed or represented by the exponential Fourier series, just like the x of n. Okay. So if we compare these two, that is a periodic signal x of n and the periodic extension of that aperiodic signal xn0 of n, we can state that XO in the limiting case, this periodic extension of x of n, that is xn0 of n, is equal to x of n when n0 tends to infinity. So the Fourier series representing xn0 of n will also represent the aperiodic sequence x of n in the limit as n0 tends to infinity. That is, in other words, we can state that as n0 tends to infinity, the fundamental frequency, here it is taken as omega 0. So omega 0 is actually equal to 2 pi by n0, and in the limiting case, as n0 tends to infinity, omega 0 tends to 0. Therefore, the separation between the successive harmonics, here it is omega 0 approaches to 0, and the spectrum becomes so dense, so it will appear as a continuous spectrum. So the discrete time Fourier transform spectra is a continuous function of omega. Next important property of Fourier spectra. Fourier spectra are periodic function of omega with period 2 pi. Now, let us consider this case, that is x of e raised to j omega plus 2 pi, omega plus 2 pi. So, by definition, this is equal to x of n into e raised to minus j omega plus 2 pi n. Now, expanding this term, e raised to minus j omega plus e raised to plus 2 pi n. We can write like this, sigma n from minus infinity to infinity, x of n e raised to minus j omega n into e raised to minus j2 pi n. And the value e raised to minus j2 pi n is equal to 1. Therefore, this is equal to x of e raised to j omega. So, in other words, we can say that the Fourier spectrum x of e raised to j omega is a continuous periodic function of 2 pi, and the periodicity is 2 pi. Periodic function of omega with the period 2 pi. Okay. So from this we can conclude that to synthesize x of n, that is from this spectrum x of e raised to j omega, we can synthesize x of n using the Fourier integral. So we need to use the spectrum over a frequency interval of only 2 pi. So starting from any value of we require only an interval 2 pi. That is, we can either use minus pi 2 pi, 0 to 2 pi, or 2 pi to 4 pi, etc. Any interval of 2 pi can be used. But as a matter of convenience, we'll choose this interval to be the fundamental frequency range, that is from minus pi to pi. And if the sequence x of n is a real sequence, then we need only to consider from 0 to pi. So, it is therefore not necessary to show the discrete time spectra beyond the fundamental range minus pi to pi. So the reason of the periodic behavior of the spectrum e raised to x of e raised to j omega is that in a basic sense, the discrete time frequency omega is band limited to pi. That is, modulus of omega is less than or equal to pi. So the maximum value is equal to pi in this case. Therefore, we need only frequency range 2 pi range. So all discrete, or in other words, we can say that all discrete time sinusoids with the frequencies separated by an integer multiple of 2 pi's are identical. Okay, so this is why the spectrum of x of n is a periodic spectrum. That is, x of e raised to j omega is a periodic function of omega with the period 2 pi. Now, about the symmetry property of DTFT. So, before stating the symmetry property of DTFT, we can define some terms. First is the conjugate symmetric sequence. Consider a sequence xe of n, and if xe of n is equal to xe conjugate of minus n, then that sequence is said to be a conjugate symmetric sequence. That is, if xe conjugate of minus n is equal to xe of n, the original sequence itself, it is said to be a conjugate symmetric sequence. Similarly, a sequence x of n is equal to minus of x or conjugate of minus n, then it is said to be an anti-symmetric sequence. Okay, now using this xe of n and x of n, any sequence x of n can be represented as the sum of xe of n and xo of n. That is, x of n is equal to xe of n plus xo of minus n. And here xe of n is actually obtained by expression xe of n is equal to half of x of n plus x conjugate of minus n. Similarly, xo of n is equal to half of x of n minus x conjugate of minus n. And another definition is a real sequence, which is a conjugate symmetric sequence, is called even sequence. That is, xe of n is equal to xe of minus n. That is, if a real sequence is conjugate symmetric, it is called an even sequence. Similarly, if a real sequence is conjugate anti-symmetric sequence, it is called the odd sequence. That is, xo of n is equal to minus of xo of minus n. So this definition can be extended to the spectrum itself. That is, x of e raised to j omega can be expressed as an even spectrum, sum of an even spectrum and an odd spectrum. So x of e raised to j omega is equal to xe of e raised to j omega plus xo of e raised to j omega. Here, the odd even part is obtained by xe of e raised to j omega is equal to half of x of e raised to j omega plus complex conjugate x conjugate of e raised to minus j omega. And the odd part xo of e raised to j omega is equal to half of x of e raised to j omega minus x conjugate of e raised to minus j omega. So this is the conjugate symmetry property of the Fourier spectrum. That is, if x of n constitute a Fourier transform pair x of e raised to j omega, and that is DTFT of x of n is equal to x of e raised to j omega, then DTFT of x conjugate of n is equal to x conjugate of e raised to minus j omega. So it can be proved like this. Consider the definition, synthesis equation. X of n is equal to 1 by 2 pi integral minus pi to pi x of e raised to j omega e raised to j omega n d omega. Now, let us find the conjugate of the entire expression, conjugate of this expression. That is, for the left hand side, conjugate is equal to x conjugate of n. Okay. And right hand side, 1 by 2 pi, integration is from minus pi to pi, x conjugate of e raised to j omega, and conjugate of e raised to j omega n is e raised to minus j omega n. Now, replace minus omega with omega. Okay. So here, we will get 1 by 2 pi integral minus pi to pi x conjugate of e raised to minus j omega into e raised to j omega n d omega. So here it is clear that the x conjugate of e raised to minus j omega is the DTFT of x conjugate of n. Comparing this expression, it is clear that x conjugate of e raised to minus j omega is equal to DTFT of x conjugate of n. So hence proved. Just like this symmetric property, we can state other symmetric property of a discrete time Fourier transform. Suppose we have this signal x conjugate of minus n, then DTFT of x conjugate of minus n is equal to x conjugate of e raised to j omega. So this can be proved using this same method. Another thing is the DTFT of real part of x of n is equal to xe of e raised to j omega. So xe of e raised to j omega is already defined. Similarly, the DTFT of j imaginary part of x of n is equal to xo of e raised to j omega, where xo of e raised to j omega is also defined. Again, if xe of n is the even part of the sequence x of n, then DTFT of xe of n is equal to xr of e raised to j omega, where xr of e raised to j omega is the real part of the spectrum. Similarly, the even part of the sequence, its DTFT is equal to j into xi of e raised to j omega, where xi of e raised to j omega is the imaginary part of the spectrum. And suppose the sequence, discrete time sequence, is a real sequence, then we can state that x of e raised to j omega, that is spectrum itself, is a Fourier transform is a conjugate symmetry. That is x of e raised to j omega is equal to x conjugate of e raised to minus j omega if the signal is real signal. Similarly, the real part of spectrum xr of e raised to j omega is equal to xr of e raised to minus j omega. So this is very important. So this states that the real part is even. Similarly, for the imaginary part is an odd sequence, that is odd one, that is xi of e raised to j omega is equal to minus xi of e raised to minus j omega. That is imaginary part is odd. And regarding the magnitude spectrum and the phase spectrum of the discrete time Fourier transform, the magnitude spectrum modulus x of e raised to j omega is equal to modulus x conjugate of e raised to minus j omega. So this indicates that magnitude spectrum is an even spectrum. That is, if the signal is a real signal, its magnitude spectrum or amplitude spectrum is even spectrum. Okay. And if the signal is a real signal, then its phase spectrum is an odd spectrum. That is, angle of x of e raised to j omega is equal to minus of angle x conjugate of e raised to minus j omega. So the phase spectrum is an odd spectrum. Now DTFT of xe of n, that is even part of x of n, is equal to xr of e raised to j omega, and DTFT of xo of n, that is odd part of x of n, is equal to j xi of e raised to j omega. And the other properties of discrete time Fourier transform. So basically the Fourier integral is a Fourier series with a fundamental frequency approaching to 0. So therefore, the most of the properties of Fourier series applies to this Fourier transform as well. One of that property is linearity property, which obeys the superposition principle. That is, if this is a Fourier transform pair x1 of n, and its Fourier discrete time Fourier transform is x1 of e raised to j omega, and the discrete time Fourier transform of the second sequence x2 of n is equal to x2 of e raised to j omega, then if we have a linear combination of these two sequences, that is a x1 of n plus b x2 of n, then its Fourier transform of that linear sequence is equal to the linear combination of the respective Fourier spectrum. That is a x1 of e raised to j omega plus b x2 of e raised to j omega. The proof is very simple. Second property is the time shifting and the frequency shifting property of the Fourier spectrum. So first, let us consider the time shifting property. For that, x of n and its Fourier spectrum x of e raised to j omega. And consider a signal x of n minus nd. That is, the sequence is delayed by nd amount. The Fourier transform of x of n minus nd is equal to e raised to minus j omega nd x of e raised to j omega. Okay, so this is proved by writing the expression for the Fourier spectrum, and from that Fourier spectrum, it is clear that there will be a term e raised to minus j omega nd. So this is an important result, and this property shows that delaying a signal by nd unit, that is x of n minus nd, delaying a signal by nd unit does not change the amplitude spectrum. Okay, that is, amplitude spectrum will be same, x of e raised to j omega. There is no change in the amplitude value of the spectrum. But the phase spectrum is changed by minus nd, e raised to minus j omega nd term is there. Therefore, phase spectrum is changed by minus nd omega. Okay, so this added phase is actually a linear function of omega with a slope minus nd. Or in other words, we can say that the time delay in a signal causes a linear phase shift in its spectrum. That is, a time delay in a signal causes a linear phase shift. E raised to minus j omega nd term is there. Therefore, time delay in a signal causes a linear phase shift in its spectrum. And this one is the last one, is the frequency shifting property. That is, if we multiply e raised to j omega 0 n with the sequence x of n, the DTFT of the entire term is equal to x of e raised to j omega minus omega 0. So the meaning is that the spectrum is shifted to omega, shifted by an amount omega 0. Next property is time reversal property. Here, if x of n and x of e raised to j omega is a DTFT pair, then x of minus n form a DTFT pair with the x of e raised to minus j omega. DTFT of x of minus n is equal to x of e raised to minus j omega. Okay, so this can be proved by replacing the n with minus n in the expression for the spectrum x of e raised to j omega. And if the signal x of n is a real signal, then this can be written as x of minus n DTFT of x of minus n is equal to x conjugate of e raised to j omega. So this is the time reversal property of the Fourier spectrum. Fourth one is the differentiation property, differentiation in the frequency domain. Let DTFT of x of n is equal to x of e raised to j omega, then n x of n, its DTFT is equal to j d by d omega of x of e raised to j omega. So to prove this, let us consider the term j d by d omega of x of e raised to j omega. Now substitute the value for x of e raised to j omega, the spectrum expression. So j by j into d by d omega of sigma n from minus infinity to infinity x of n e raised to minus j omega n. Now finding the derivative of this term, you will get minus j n term will be there. So this equation become j sigma n from minus infinity to infinity x of n into minus j n into e raised to minus j omega n. Now j into minus j is equal to 1. Therefore, this will become summation n from minus infinity to infinity n x of n e raised to minus j omega n. So this expression states that this will be the Fourier transform of this term n x of n. That is, Fourier transform of n x of n is equal to j d by d omega of x of e raised to j omega. So that's proved. Next is the convolution theorem. Let us consider two sequences x of n and h of n, and let x of e raised to j omega and h of e raised to j omega be the respective discrete time Fourier transform spectrums. Then Fourier transform of x of n convolution h of n is equal to x of e raised to j omega into x of h of e raised to j omega. That is, convolution in time domain transforms to multiplication in the frequency domain. Okay, so DTFT of convolution of two sequence is equal to the product of the respective spectrum. Proof. First, let us write the expression for DTFT of x of n convolution h of n. So for that, this outer summation is for finding the Fourier transform DTFT equation. So inner summation is for finding the convolution. So inner summation from k from minus infinity to infinity x of k into h of n minus k is equal to x of k convolution h of n minus h of k, and e raised to minus j omega n to find the DTFT. Now let us substitute this value n minus k with m. Therefore, n is equal to m plus k. Now, writing this, substituting n minus k with m, this can be written like this: summation m from minus infinity to infinity. Okay, that is, if we substitute n minus k with m, n is equal to m plus k. Therefore, here the outer summation becomes m from minus infinity to infinity, and the inner one summation k from minus infinity to infinity x of k into h of m. Now here n is replaced with m plus k. Therefore, e raised to minus j omega m plus k. And this e raised to minus j omega m plus k can be written as e raised to minus j omega m and e raised to minus j omega k. Okay, now rearranging this expression, we can write like this: summation k from minus infinity to infinity x of k e raised to minus j omega k into summation k from minus infinity to infinity x of n. Here it is summation m from, not k, m from minus infinity to infinity h of m into e raised to minus j omega m. Now, this expression is the analysis equation for the sequence x of k, that is DTFT spectrum equation. So this is equal to x of e raised to j omega, and this one is equal to h of e raised to j omega. Therefore, x of e raised to j omega into h of e raised to j omega. That is, DTFT of convolution of x of n and h of n is equal to the product of the respective spectrum. Next property is Parseval's theorem. Suppose we have two sequences x of n and y of n, and their respective spectrum be x of e raised to j omega and y of e raised to j omega. Then summation n from minus infinity to infinity x of n by conjugate of n is given by 1 by 2 pi integral minus pi to pi x of e raised to j omega into y conjugate of e raised to j omega d omega. So this is Parseval's theorem, and the special case of this Parseval's theorem is if you substitute y conjugate of n with x conjugate of n, this will become sigma n from minus infinity to infinity modulus x of n square, that is its magnitude square value, which is nothing but its energy. This is equal to 1 by 2 pi. This one will become y x of e raised to x conjugate of e raised to j omega. So this will become modulus of x of e raised to j omega square. So this is the special case. Now this Parseval's theorem can be proved like this. Let E is equal to the first term. Let E is equal to LHS sigma n from minus infinity to infinity x of n y conjugate of n. Now we all know that DTFT of x of n is equal to x of e raised to j omega, and DTFT of y of n is equal to y of e raised to j omega. Therefore, this x of n can be write like this: 1 by 2 pi, its synthesis equation, 1 by 2 pi integral minus pi to pi x of e raised to j omega n d omega. Now E is equal to x of n y conjugate of n, or this summation. Now we are going to replace x of n with this equation: 1 by 2 pi integral minus pi to pi x of e raised to j omega n d omega. Therefore, E is equal to sigma n from minus infinity to infinity 1 by 2 pi integral minus pi to pi x of e raised to j omega n d omega, that value, into y conjugate of n. Now rearranging this one, that is changing the order of summation and the integration. So x of e raised to j omega term will be outside because there is no dependency on this n value. Therefore, 1 by 2 pi integral minus pi to pi x of e raised to j omega, and taking summation term inside, we'll get sigma n from minus pi to pi y conjugate of n e raised to j omega n d omega. Now this value summation n from minus infinity to infinity y conjugate of n e raised to j omega n is nothing but the spectrum y conjugate of e raised to j omega. Therefore, E is equal to 1 by 2 pi minus integral minus pi to pi x of e raised to j omega y conjugate of e raised to j omega d omega. So that's proved. And the term in this special case, the term x of e raised to j omega square modulus square is actually called the energy density spectrum of the signal. And the Parseval's theorem is also called Rayleigh's energy theorem. Next is the modulation property of discrete time Fourier transform. Suppose DTFT of x of n is equal to x of e raised to j omega, and DTFT of w of n is equal to w of e raised to j omega. Here this w of n is a windowing function. So this windowing function is actually used to find the finite response from the infinite impulse response. That is, in order to truncate the infinite impulse response, we'll multiply that infinite impulse response with the windowing function. So let x of n into w of n is there. That is, discrete time Fourier transform of x of n and w of n is given by x of e raised to j omega convolution w of e raised to j omega. So here x of e raised to j omega convolution w of e raised to j omega is the periodic convolution. So if you multiply two sequences in time domain, it will transform to convolution in the frequency domain. So x of e raised to j omega, the periodic convolution x of e raised to j omega and w of e raised to j omega is equal to 1 by 2 pi integral minus pi to pi x of e raised to j theta w of e raised to j omega minus theta d omega. So this is the periodic convolution of x of e raised to j omega and w of e raised to j omega. The proof is, let us write like this: w of e raised to j omega minus theta. Okay, the spectrum value is equal to e raised to j omega minus theta. Therefore, this can be written like this: w of n into e raised to minus j omega minus theta into n. Okay. Now, x of e raised to j omega in convolution w of e raised to j omega. So by definition, from the previous slide, it is defined here, periodic convolution. So this one, x of e raised to j omega convolution w of e raised to j omega is equal to 1 by 2 pi integral minus pi to pi x of e raised to j theta. Now substitute this one from this expression. Here w of e raised to j omega minus theta is there. So in place of that w of e raised to j omega minus theta, substitute this value. So you can write like this: w of n e raised to minus j omega minus theta into n d theta. Now rearranging this equation, changing the order of summation and integration, you can write like this: summation n from minus infinity to infinity, w of n e raised to minus j omega n, then 1 by 2 pi integral minus pi to pi x of e raised to j theta e raised to j theta n. So this can be written as sigma n from minus infinity to infinity x of n w of n e raised to minus j omega n. So this one is actually the synthesis equation for x of n. Okay, w of n is there and e raised to minus j omega n is there. So we can state that the Fourier transform of this product x of n, w of n is actually equal to x of e raised to j omega convolution w of e raised to j omega. So multiplication in time domain transforms to convolution in the frequency domain. So in DTFT, discrete convolution of two sequences is the multiplication of the two periodic spectra. And the multiplication of the two sequences is the periodic convolution of the periodic spectra. Okay, so convolution in one domain transforms to multiplication in another domain. The final property is correlation theorem. Suppose x1 of e raised to j omega is the DTFT of x1 of n, and x2 of e raised to j omega is the DTFT of x2 of n, then the correlation, cross correlation Rx1 x2 of m, this is the correlation function. The DTFT of this correlation function is Sx1 x2 of e raised to j omega. So here this Sx1 x2 is actually the cross energy spectral density. Okay. Therefore, this Sx1 x2 of e raised to j omega is equal to x1 of e raised to j omega into x2 of e raised to minus j omega. And the cross correlation Rx1 x2 of m is defined as summation k from minus infinity to infinity x1 of k into x2 of k minus n. Okay, so please spot the difference between the expression for convolution and the expression for this correlation. Okay. So the special case of this correlation theorem is that if we find the autocorrelation instead of this cross correlation, if we find the autocorrelation, it will be like this. Special case autocorrelation Rx of m, its Fourier transform is equal to Sxx of e raised to j omega. So this autocorrelation function and this power spectral density forms a discrete time Fourier transform pair. So this expression is also known as Wiener-Khinchin theorem. That is, a power spectral density is found out by finding the Fourier transform of the autocorrelation. So these are the properties of the discrete time Fourier transform. And as I said earlier, this Fourier integral is basically the Fourier series with a fundamental frequency that is let us take it taken as del omega, this fundamental frequency approaching 0. So in a sense, Fourier transform is a Fourier series where the fundamental frequency is 0 or infinitesimally small. So all the properties of the Fourier series applies to this Fourier transform as well. Okay. So thank you.